Okay, let's dive in. We're unpacking something really fundamental today about special relativity, specifically how things look when they move incredibly fast. It's called the Terrell-Penrose effect.
That's right.
And our mission here is to correct a pretty common misconception, the idea that if you saw a sphere zip past near light speed, it'd look flattened, squashed like a pancake.
hmm Exactly. That mental image, while maybe intuitive based on textbook diagrams of Lorentz contraction, it's actually not what you'd visually perceive.
Right.
And this isn't brand new thinking, though it took a while to catch on. Anton Lampa first touched on it back in 1924, thinking about a moving rod.
1924. Wow.
Yeah, but it was kind of overlooked. It wasn't until 1959 that Roger Penrose and James Terrell independently really formalized the visual geometry.
Wow.
Terrell's paper title I always like, Invisibility of the Lorentz Contraction. Quite provocative.
Invisibility. Yeah, that is bold. Because the length contraction is physically real, right? The object does get shorter in its direction of motion according to measurements in the observer's frame.
Absolutely. The physical contraction is real. That's core special relativity.
So why is the visual interpretation the squashed sphere? Why is that wrong then, if it's physically contracted?
Well, the mistake is forgetting about light travel time. I mean, for you to see the object, light from all parts of it has to arrive at your eye or your camera at the very same instant to form that snapshot image.
Okay.
But the object's moving extremely fast. So the light from the back end, the trailing edge, has farther to travel to reach you compared to light from the front end.
Right, because it's further away when the light loses it.
Precisely. So for that light from the back to arrive simultaneously with light from the front, it must have been emitted earlier.
Ah, okay. And because the object keeps moving.
Exactly. During that extra travel time for the light from the back, the object itself has moved forward, moved out of the way, effectively.
So the light from the back seems to come from sort of behind where the object is now.
You've got it. Penrose showed this geometry really clearly. For a sphere, this effect, seeing the trailing parts from an earlier time and skewed angle, makes it look elongated in just the right way.
Elongated, but I thought it was contracted.
Physically contracted, yes.
Yeah.
But this visual elongation, due to the light travel time, exactly cancels out the appearance of the Lorentz contraction. So the sphere's outline still looks perfectly circular. What you perceive visually is more like a rotation.
A rotation, not a squashing. That's quite different.
It is. And for decades, this was, a theoretical prediction. We had simulations showing it, but no direct observation.
Until recently, right? I saw this 2025 paper by Hornoff and colleagues.
Yes, exactly. Just this year, a genuine laboratory experiment finally demonstrating the effect. 100 years after Lampa's first thoughts. Remarkably.
So how did they do it? They obviously didn't accelerate a real sphere to 0.9999 C in the lab.
No, definitely not. They used a really clever high-speed photography technique. Think picosecond laser pulses and incredibly fast camera gating times, shutting the camera's eye in as little as 300 picoseconds.
300 picoseconds? That's unbelievably fast.
It is. They use what's called time-of-flight imaging. They took a model object, say a sphere or a cube, that was already physically shaped as if it were Lorentz contracted.
Okay, so they pre-squashed the model?
Sort of, yes, to represent the physical state. Then, using these ultrafast laser pulses and gating, they selectively illuminated and imaged different parts of this model with precise time delays, mimicking the different light travel times that would occur in a real relativistic scenario.
So they built the light travel delay into the imaging process itself.
Precisely. By doing this, they effectively simulated the relativistic viewpoint. It's like they virtually slowed down the speed of light in their setup to less than 2 meters per second, which makes these relativistic visual effects large enough to capture.
That's ingenious. And the results?
They confirmed the theory beautifully. They synthesized snapshots. For their model sphere moving at a simulated 0.999 C, the snapshot showed a circular outline.
That's squashed.
Not visually squashed. And they did a cube too, at 0.8 C. The physical model they used was contracted, as expected by Lorentz, with an aspect ratio of 0.6. But the final image...
Let me guess. It looked like a normal cube, just rotated.
Exactly. A visually rotated, non-contracted cube. It's really compelling evidence that what you see is dominated by these light travel time effects, leading to apparent rotation, not just the physical contraction.
Wow. It really changes how you picture relativistic travel.
Okay, that brings us neatly to the end of the core discussion, but before we wrap up, a quick word from our sponsor. Today's deep dive was brought to you by embersilk.com. Embersilk is the answer for all your AI education and integration needs. Check them out at embersilk.com. And thinking about this experimental technique, It really opens up possibilities, doesn't it? It makes me wonder, and perhaps something for you, the listener, to ponder,
Well,
if we can use this method to visualize the Terrell-Penrose effect by effectively slowing down light.
hmm.
What other classic relativity thought experiments could we finally visualize? Could we perhaps create a visual demonstration of the famous train and tunnel paradox, or something that truly shows the constancy of the speed of light in a way we can, well, see?
That's a fantastic thought. Moving these concepts from pure thought experiments to something visually demonstrable. What else could we finally see? A great point to end on. If you enjoyed this deep dive and got something out of it, please do remember to subscribe wherever you get your podcasts, and leaving a 5-star review really, really helps us keep these explorations going. Thanks for joining us.